Hello, hello, everyone. I hope that everyone is doing well today. Good afternoon. Happy noon. Today we are going to be continuing with our introductory lecture series on the C programming language. Now, yesterday we talked a lot about integers. Integers were the main focus of yesterday's lesson, where we started off discussing the sizes of the various integer types in C, of which, of course, we learned there are many. We talked about the notion of signedness and the 2's complement arithmetic system that comes with the notion of signedness in the C language. And we also talked about the bitwise operators in C, the operators that operate not only on numbers for their arithmetic values, but also for their values as binary sequences, as just sequences of zeros and ones, or bits. And today, we're largely going to be talking about other types in C. Integers are not the only things we can work with in C. Unlike some of the older languages that we talked about yesterday, we can also manipulate numbers as things like decimals or floating point values. We can manipulate values in terms of whether they are Booleans, and we can even structure our data in C, kind of like we might a class in Java. But today we're actually going to begin by talking a little bit more about integers, just a little bit. And that's because we have another very fundamental concept that we need to discuss before we launch into the remainder of the C language. And what we are going to be discussing today, just to begin, just for a few minutes, is the notion of Endianness. So, Endianness, spelled with an E like this, refers to the way in which the bytes in integers are arranged in memory. And so, you might kind of say, you know, what on earth does that mean? I mean, we know that, every value that we're working with on a computer, by and large, is going to have some type of memory representation. But we haven't really ever dove into exactly what that representation is. How are numbers represented in memory? Well, let's begin by taking another example, a lot like the one that we worked with yesterday. So we talked about how really numbers are just sequences of zeros and ones, of bits, on bits, and off bits. And we talked about how we convert numbers between different bases, and specifically how we can convert decimal numbers into binary. And the example that we mostly worked with yesterday was the unsigned integer 47. And we said, okay, so 47 in base 10, which we worked with primarily as an 8-bit quantity, which we're going to have to get away from a little bit at the beginning of today's lesson, but not too much. So 47 is an 8-bit quantity. We said we were going to convert to binary by simply considering the place values of each binary digit that makes up this number. And so let's say that we're converting 47 as an unsigned integer, meaning that our powers of 2 to the n, that's a bad n, are still going to proceed from 0 up to 7. And our values for our powers of 2, which we'll go ahead and write out one more time today, just to review, would be 1, 2, 4, 8, 16, 32, 64, and 128. And we said we would convert our number thusly. We would proceed from the most significant bit, which is going to be this leading bit up here, so the bit with the highest place value, which we call the MSB, most significant bit, all the way down to the LSB, the least significant bit, down here, the bit with the lowest place value. And we would say every time we encounter a bit, we're going to determine whether its place value is less than or equal to the number that we are trying to convert. And if it is, then we're going to write a 1. And if it's not, then we're going to denote a 0. So we can go ahead and start converting our number. You say, all right, so 128 is greater than 47, so there are no 128s that go into the number 47. And so we're going to write a 0 for that place value. 64, same thing. No 64s can go into 47. 64 is larger than 47. So we're going to write a 0. 32, on the other hand, is less than 47. And so we can have a 32 as constituent in 37. Or I'm sorry, in 47. And now what we're going to do is we're going to subtract that 32 from 47, just to say, hey, this is how much of the number I have left to represent in my binary string. And we said, okay, so we're going to subtract 32 from 47. We'll get a value of 15. I accidentally undid my 1 there. And then we'll proceed the same way. There are no zeros that go into 47, or into 15. No zeros that go into 15. An 8 can go into 15, leaving 7 over. A 4 can go into 7, leaving 3 over. A 2 can go into 3, leaving 1 over. And a 1 goes into 1, leaving 0, and indicating that we did our conversion successfully. Now, the reason that I want to go over this is, well, it's twofold. It's first that I just want to make sure that everyone really understands this concept of converting from decimal to binary before we move on too much. It's going to be very important for us moving forward. But also because this concept of most significant and least significant is going to become a pretty big deal as we discuss the concept of Endianness. And so I'm just going to note here what this means. MSB is most significant bit. And LSB is the least significant bit. And when we talk about significance here, we don't really mean how important these values are, although, I mean, you could say that values that are larger have, or just bits that are larger have more value. That would be a very capitalist way of looking at things. But we're going to say that the most significant and least significant really denote highest place value for most significant. So this is highest place value. And the LSB, least significant bit, denotes the lowest place value. And now yesterday, as we were working with these numbers, we stuck with 8-bit quantities. Firstly, because they were easy for me to work with. They didn't require much writing in order to actually represent, which is, you know, always preferable. But there's another advantage to them, and that is that we did not need to deal with Endianness. So to start off, let's go ahead and define now, as we move on to how we might represent larger values in memory, this concept of Endianness. So Endianness refers, as I said earlier, to the way in which bytes are arranged, the order in which bytes of a value are arranged in memory. And so now let's go ahead and let's pick a bigger number. Now we're going to work with a base 16 number for this, and we'll talk about how to work with base 16 or hexadecimal in just a little bit. But for now, all we need to know that in hexadecimal, if I write a number like this, so let's say that I'm going to write a number with the digits, let's go with Beef Cafe. This is a base 16 number. And it has some binary value, I'm not really fully sure, or some decimal value as well, I'm not really sure what that is, but we're just going to work that as a hexadecimal number for now. And all we need to know is that in hexadecimal, every 2 digits represent a single byte. And so the BE is a byte, the EF is a byte, the CA is a byte, and the FE is a byte. And so altogether, this number, this value, requires 32 bits to accurately represent. And so this entire thing here goes down to 32 bits. Or 4 bytes in total. And now if I want to show you how these bytes are laid out in memory, or if I even just asked you, how are these bytes laid out in memory, I almost guarantee you would tell me, well, what do you mean? They're laid out exactly like you wrote them, right? And so now if we move on to a representation of memory, in which each square is now not a bit, but a byte. Oh, don't need that fourth one. Then I almost guarantee that you would assert that, well, this number is laid out like this. In memory, we would have BE, then EF, then CA, and then FE. Where the beginning of this block that we've written, so the beginning of this is going to be the lowest address in memory, and this end is going to be the highest address in memory. And, you know, that would kind of sort of make sense, right? We talk about memory going from, you know, for example, so we might have the beginning of this integer as offset, let's just say that it's at, I don't know, offset 64, and then the end of this being at offset 68. And so we just, as we proceed through memory, we move on and we denote each byte of our number in sequential bytes of memory. And hey, that totally makes sense. And it turns out that it's probably not how the computer that you're watching this on right now does things. We've got a question from Prince Logic. What if you have an odd number of letters? Right, well, so if we have an odd number of letters, then something very similar is going to happen to what we talked about with our number 47. 47 did not fully occupy the 8-bit space that we were using up here, right? There were actually 2 bits, ahead of 47 that we had to pad with zeros to indicate that there is no value there. We would do a similar thing if we had an odd number of letters. And so, you know, if we had something like, I don't know, if we just had, you know, let's just say we had BEEFCA, then we would write it as, oh, well, that didn't work. Then we would end up writing it as 00BEEFCA, padding out the beginning of that number with zeros, just to indicate that there is no value in that place. Okay, great. So now that we've got that handled, yeah, let's come back to this example. So I told you that we would lay out these digits from low address to high in the order in which they come. So just digits laid out sequentially in memory, or bytes laid out sequentially in memory, just like we would think of it. And that's not how your computer probably does it. And the reason for that is that we refer to this scheme of the low addresses going up to the high addresses, so where the most significant byte, which we'll denote MS capital B, down to the least significant byte, LS capital B, laid out sequentially in memory, we refer to as as big Endian byte order. And wow, that's a mistake to make. Yeah, so we refer to this as big Endian byte order. So this is big Endian. And the easy way to remember the difference between big Endian and the other scheme that we're going to talk about in a minute is that in big Endian, the byte with the biggest place value, the most significant byte, comes first. That's the easiest way to remember it. We say the big as the first thing in big Endian, so the biggest byte, the byte with the biggest value, must come first. And Bright Knight says, that's why we have the pseudo EOF value in Huffman. So yeah, so you're referring to the Huffman coding assignment in which we asked you all to write a encoder and decoder for the Huffman compression scheme. And it's somewhat similar to why we had to have a pseudo EOF in Huffman. And more specifically, it's similar to why we had to, why that pseudo EOF had to be 9 bits instead of 8 bits. We just had to make sure that that value lied outside of the potential value space for our for our letters, right? For the characters, the ASCII characters, 8-bit characters we were dealing with. So it's somewhat similar, but not exactly the same. Okay, so yeah, so this is a big endian byte ordering scheme. And there are lots of machines that use big endian byte ordering schemes. Namely, a bunch of mainframes do this. So, you know, the really, really big computers by IBM that back probably your bank and a bunch of other things that are programmed largely in COBOL and other old kind of decrepit languages are largely using big endian byte ordering schemes. Those are the main users of big endian nowadays. However, there are also some architectures that we'll talk about in a minute that may use big endian in some circumstances, but we will get to that. But now, I would like to note that this way that we wrote it up here is not the only way that we can represent this number in memory. There's actually another way that we can represent this number, Beef Cafe hex, in memory. And it looks something like this. So, you know, we're still... Let me write this one line down, actually. We're still going to have our 4 bytes. And their addresses are going to proceed in the same way, where we're going to go from low address to high address. That's just how we represent memory. And I'll even give them the same offsets. So this is offset 64. This is offset 68. And now the difference here, the difference between this scheme that we are about to work with and the one we worked with above is how we lay out the bytes in memory. So on the previous example, we proceeded from most significant byte to least significant byte as we advanced through memory. In this one, we're going to go the other way. So we're actually going to start by writing the least significant byte first and proceed to the most significant byte. And now this is kind of tricky to wrap your head around at first. So the way that we're going to convert this number to our alternative encoding scheme that we've got written down here is we're going to start off with the least significant byte and advance up to the most significant as we go. So we're actually going to start off with the least significant byte, FE, and then move on to the next, CA, EF, and BE. And now you might be like, why would we do this? This is actually a somewhat confusing way of doing things. And you know what, you're partially right in saying that. But the thing that we need to contend with is also that this is actually the most common way nowadays that computers represent numbers in memory. This is an encoding scheme that we call little endian. And little endian is used by, well, pretty much everything, actually. It's the primary encoding scheme that's used by the x86 architecture, which is probably what's in your PC currently. Again, unless you have something like an Apple Silicon Mac, it's probably running x86. So this is, you know, most computers. And it's also the primary operating mode for ARM on Linux. And so this is, yeah, so Linux on ARM, which, by the way, includes Android. It's also the primary operating mode for Mac OS and iOS and tvOS and all of the other Apple operating systems. And so yeah, if you are working with a number in memory, you are almost definitely working with a little endian value nowadays. And so yeah, so this is the concept of endianness. It's something that's very important to know because it can actually affect your programs. So let's say that we are trying to write this number, Beef Cafe, over the network. I am trying to blast this number, Beef Cafe, to another computer over a network, right? I'm trying to send it at, you know, over a WebSocket or something like that. And I want to say, hey, other computer, somewhere off and who knows where, I want you to receive this number. Now, the issue that we might run into in doing this is that if I stick with my machine's native byte ordering of little endian, then there are two potential ways that that target machine could receive that number and interpret that number. It could realize that, hey, this is a little endian value. I'm a little endian machine. I thus am capable of decoding this number correctly and getting this value that we wanted, Beef Cafe. However, if I send this number over the network as a packet, and it's received by a big endian machine, then that machine is quite liable to instead read this number as this hexadecimal value. It's going to decode it as big endian. And this is obviously wrong. So, we have to standardize the way in which we are going to send values over the network. And this is why sometimes you may hear big endian also referred to as network order. So yeah, for a while, it was not exactly clear which Endianness most computers would be using, and so back in the days of, mainframe computers and whatnot, and even, before that, I'm talking about, back in the days of the ARPANET, the precursor to the internet, we standardized on big endian, or network order, byte order, for sending things over the network just because it was more common at the time and supported by more hardware at the time. And Blue Jay has a question, why did we start at 64? And I think you're referring to the address of our number, the kind of address we made up in memory for our number, and it's completely arbitrary. It's really just to show you that, these values actually do progress through memory. Each byte has a subsequent address in memory. And yeah, it's totally arbitrary. I mean, we honestly probably could have used Beef Cafe as an address if we wanted. We could have used anything. 64 is just the first number that came to mind. So yeah, don't, the first even number that came to mind, because they're a little easier to work with. So yeah, it's arbitrary. But now the thing to note about this, about our byte ordering, is that it can affect how other machines interpret values. However, it is not going to affect how our machine interprets values. And so what that means is that if I now switch over here to our IDE, and I'm going to write a very simple C program. So I'm going to call this endian.c. I do not want it to be a C++ file. We're going to go ahead and add it to CMake just so that we can build it. Again, not something that you need to know, just something we've got to do to get binaries building. And so now what I'm going to do is I'm going to write a really, really simple program. And what this program is going to do is it's going to get that number that we were talking about earlier, which we're going to call sample. And note that in C, we can write a hexadecimal number by preceding it with this prefix 0x. And now this is telling me it's upset that we never... Oh, that this is an unsigned value, so that's fine. I'll just go ahead and write this as unsigned. And now what I'm going to do is I'm going to print an expression in hex. And what I'm going to print is sample and not xff. Unsigned. So now what this means here, sample and not xff, is it really means that we are going to AND this value, BEEFCAFE, with this value. So we're going to do our bitwise conjunction on these two values. And the result that we get from a masking FF, which is really just a series of 8 ones, with our number, is that we're going to extract the lowest order byte. Which sounds all well and good. And so, since I told you earlier that we are running this on a little endian x86 machine, you may expect, and you would be correct in expecting, that in memory, this value here, this Beef Cafe value, is laid out FE CA, EF, BE. Exactly the same way that we wrote it on our handout here, FECA, EF, BE. And so you may expect that ANDing this value with not x FF would return BE in hex. So let's go ahead and test that now. Oh, and we'll go ahead and give this a return value just to be good programmers and good engineers and make sure that, you know, our code is easily interpretable. So yeah, let's go ahead and run this now. All right, we're going to switch to binary endian and run. And we get not x, FE. Oh, that's interesting. Why might that have happened? Well, so we talked about this a little bit yesterday. And we discussed yesterday very, very briefly, and I really just kind of name dropped it, the concept of the C abstract machine. So the C abstract machine is essentially a definition of kind of an imaginary computer that is running your C program that sets certain rules about how your program might run. So the C abstract machine, which we'll go ahead and write here, the C abstract machine, is defined to treat values as if every number you receive is is big endian. And you know, this actually kind of makes sense, right? It makes sense that this is big endian because that's how we work with numbers. That is how our number system works. If I write a number like 437,863, we start off this value with the most significant digit and proceed to the least significant. And so the C abstract machine is defined as big endian so that when we do bitwise operators like the one we did above, where we said that we're going to take BE, and here, let me draw this out for us. So where we're going to take, let's see here, how big do I want to make this? Yep, that'll work. Oh, that's wrong. So where we're going to take a value like our beef cafe, can't write today, my apologies. We're going to take a value like B, E, F, C, A, F, E, and that value with 0xFF, which we're going to, as we discussed earlier, pad with zeros. We are always, no matter what the endianness of the actual machine we're running this on, going to get a return value of not x 0, 0, 0, 0, 0, 0, FE. And this is just another aspect of C's portability, that no matter whether the machine that you are writing your code on and compiling your code on and compiling your code for is big endian or little endian, we are always going to get the same result. And so yeah, that's just kind of a cool aspect of C. And we can see the very same thing that if we were to try and, let's say, right shift a number, then we would really be right shifting the big endian representation of that number, not the little endian representation, which again is going to exhibit the kind of behavior that we would expect of right shifting dividing by a power of 2. And Prince Logic, does the FF matter? It doesn't really matter too much. We just used FF here because FF is a number, right? It's a series of 8 ones, value 255, that we can use to mask out bytes. And so whenever we are doing byte masking, where we're trying to extract a single value from a number, and you make a good point that we should probably point this out, that this masks out the byte. It's a byte mask. So yeah, whenever we are masking out a value using the AND operator, trying to extract a particular byte or series of bits from a number, we're going to use probably some derivative of ff. We might add more f's. We might have to do some shifting. It's really going to depend on the values that we're working with. But yeah, that's how we're going to extract bytes in C. Okay, great. So yeah, so that is really all I want to talk about with integers today. This is really the last major concept that we need to know how to work with in order to understand integers in C. So now I would actually like to move on to something else, which is we're going to talk about the other types that C has. So previously we've been working exclusively with integers, and there's good reason for that. A lot of the times the types of programs that you're going to be writing in C are what we would consider system software. It's, you know, code that's going to be running at a lower level, and a lot of the time low-level code just does not need things like floating point values, decimals. You just don't need that. But C does provide support for them, so we'll talk about them very briefly. And we're not really giving them their due time, because especially some of these are incredibly complicated. And we'll circle back to how some of them work, but for now, while we're just learning how to write some C, I'm not going to belabor it too much. So let's go ahead and add another program. All right. So what we are going to be doing now is exploring, as I include some standard headers here, we're going to be exploring the floating point types in C. So you may remember floating point types from Java. So the floating point types we had in Java were called float. And, you know, we'll say float, a number that we could represent is, I don't know, we'll just say pi, right? Which would be 3.14159.265, something like that. And does that overflow a float? It does. So we're actually going to reserve that for a double. And, you know, we might have a float, something like, you know, 1.5. And in Java, we told you that, in general, doubles are preferable to floats. And the reason that we told you that doubles are preferable to floats is because doubles had a higher precision. Notably, they had double the precision of a float. Pretty straightforward naming here. Pretty straightforward naming. And so, yeah, and what is this unhappy about? We're going to ignore that. And anyway, so when we are, talking about floats and doubles, the only thing that we really need to know is that a double has double the precision of a float. Now, what precision means relates to the way that these values are, again, laid out in memory and interpreted by your processor. On all of the CPUs that we use nowadays, floating point values are represented using a standard that we call Ieee 754. Now, Ieee is the organization that essentially regulates most of electrical engineering, and they also are involved somewhat in the CS regulation space. And I'll note that, you know, this regulation is also cross-listed with other organizations like ISO, the International Standards Organization. But anyway, this is a standard that was developed to describe how your computer can represent floating point values. We are going to talk about how Ieee 754 works on another day. We are not going to get into that today because it would take up the rest of our time, and I really want to get on to something that's a little bit more interesting and a little bit more important for you as a C programmer. And so, yeah, we're not going to dive into this, but just know that a float has twice the precision of a double. And we can actually see that if we just try and print out. So the first thing we're going to do is print out our float. And I want to do with this float is I'm just going to print out its size. And so, yeah, the size of our float, and then we're going to print out the value itself, which uses the notation %f. And so we're going to print out the size of the float, and then the value itself. And I'll note here this macro, well, it's not really a macro, it's more of a directive, size of. What this does is when your C compiler encounters this directive, size of some type, it returns the number of bytes that that type occupies. And so, you know, just to start off, if I printed something that we already know, if I printed the size of an int, then you'll see that, you know, on my modern system, that's going to print, if I run the correct program, that is going to print 4, right? 4 bytes. 4 bytes to an int. So now we can do the same thing with our float and our double. So I'm going to print my float, I'm going to print my double, and we can see how big both of these types are. So we'll run our program here and we'll see, okay, my float occupies 4 bytes in memory. And you can see here's the value of our float. And my double is going to occupy 8 bytes in memory, and there's its value. Although I believe I've made a little bit of a mistake here. I think I accidentally printed that as a float and not a double. Well, no, it's the same. Okay, whatever. Anyway, again, I don't work with these very much. The last time I worked with a floating point value was like years ago. I'm a systems engineer. I don't touch these. Anyway, so yeah, so a float is 4 bytes long, a double is 8 bytes long. Again, double is more precise than float. Sometimes you'll need that precision, sometimes you won't. It's not really something we're gonna get into. But one more thing that I would like to note that is a little bit more important is what happens when I do this. So let's say that I am going to print float plus double. And we're going to determine what happens when we do that. So yeah, so what is the size of adding a float and a double? Well, let's figure that out. So I'm going to add some value and pi. And now the reason that I've written this inside the size of and duplicated it, I know it's bad programming style, but that's because I don't want to reveal what type this number is going to be yet. So now if we compile and run this again, then we'll see that when we added our float and our double together, we got a result that was 8 bytes long, or in other words, we got a double precision float. And the reason for this is, again, the same thing that we discussed yesterday, that in C, when you have operands of different sizes, both operands are going to be promoted to the largest, well, in this case, the larger type. And so since double here is 8 bytes long, float is 4 bytes, we're going to promote our float here to a double in order to perform this addition. Oh, and Prince Logic has a good question. What does the U mean after %Z? Right, so this is really just kind of printf language. So printf is kind of a domain-specific language of its own in C. But what this really means is the %Z means that we're printing a size. Z refers to the type that is used in C for sizes. And the U says that this value is unsigned. And so since we know that this is never going to be negative, we can just go ahead and say, okay, I know that size of outputs an unsigned value, so we're just going to mark this as unsigned. And if we leave that off, and actually what we can do to get a little bit more practice with this today, which would probably be good, is let's go ahead and compile our C program from the command line and see what happens if we leave off that U. So I'm going to go ahead and pull up a command line here. See, here's our current folder. Well, there's an old version. There's our current folder. We're going to compile our program. And remember that the way we do that is we type cc, and then we're going to type the name of the file that contains our main function. And when we get into multi-file projects, this is going to change. But for now, we're just going to type the file that contains the main function. And we're going to output this to a binary called other_types. And we see, oh no, we get this kind of scary looking compiler warning. And the warning that we get here is, oh, it's not actually quite what I was expecting. Let's change this. And let's say that we're just going to treat this as an int. Here we go. We're going to treat this as an int. my C compiler is warning me. It says, hey, format %d expects an argument of type int, but you gave it an unsized. And I will, or sorry, a long unsigned int. Unsized, a long unsigned int. And so what happens is we don't really know what the return value or what the return type of the size of directive is. So our C compiler instead designates, hey, I'm going to give you its own type, which in printf we represent with %zu. And so if we compile this now, we see that there are no warnings. And if we run it, we get the result that we were expecting. Okay, great question, great question. And so yeah, so this is floating point in C. Honestly, we're not going to talk any more about it today because we don't really need to. That's all you really need to know to write C programs. Now, when we get into the more kind of computer architecture aspects of things, we're going to go a little bit deeper and talk about how these things are represented in memory the same way we did with ints. But for now, not important. So, let's go ahead and move on to our next type. Booleans. Now, prior to recent C standards, this would be an extremely simple section. What I would tell you is in C, here's how Booleans work. Booleans are just integers. If the integer has a value of 0, then that Boolean is falsy. And if it has a non-zero value, then that Boolean is truthy. Done. Yay, cool. That was easy, right? Not too much to really worry about here. Unfortunately, that's not true. This is how Booleans were represented in C for a really long time. Believe it or not, in C, I can say something like, you know, int test, or, I don't know, I'll call it int condition equals 7, and I could say if condition, printf, %d is true. And I'll say else %d is false. And if we run this, then we'll see that when I type in 7, it says that, hey, 7 is truthy, as we were expecting. It's a non-zero value. And if I set condition to 0, then it's falsy. And that's it. That's how Booleans work in C. It's really straightforward. And so a lot of the time in Java, you may have noted that we had to write things like, you know, if condition is double equal to 0, then we have to do some stuff. Right? We had to very explicitly convert our integer to a Boolean. And Prince logic, we'll get there. We'll get there. And, you know, this system works really, really, really well until we get to something that we talked about yesterday, which is undefined behavior. So remember that lots and lots and lots of things that actually happen in C, it is not defined what behavior they exhibit when these conditions occur. And one of these is integer overflow. So let's say that I'm going to now change condition to type unsigned char. So it's going to be an unsigned 8-bit value. And hey, you know, I can still say, and C-Lion is even telling me, hey, this is a trivially true condition. Or a trivially false condition, sorry. This is 0. And you know, if I set this to 0, then I'm going to get the same thing that I was expecting, that it's false. And let me go ahead and comment out these other printfs, just so that it's a little bit easier for us to read the result. And you know, if I set this back to 7, then we've got a trivially true condition. Cool. Huh. So, this is a little bit of an edge case. So what we're doing now is we're assigning the value 256 to type unsigned char. Now, you may remember from yesterday that the range of unsigned values of n bits goes from 0 up to 2 to the n minus 1. Meaning that for an unsigned char, our range of values is 0 to 255. Okay. So what happens if we assign 256? Well, let's see. So we're expecting, okay, 256, you know, hey, that's a non-zero value. It's going to be truthy. That's trivially true. Why are we even running this example? This is dumb. Oh. Well, that's not good. That's not good. My 256 has died. It's telling me that my 256 is false. And in fact, it told me it's 0. What on earth is this? This is nonsense. This is dumb. Well, here's the problem. Remember in Java, we talked about this really, really briefly, and most Java programmers talk about this very, very briefly. If you have a really, really, really big number, let's say that you have integer.maxValue, and you add 1 to that value, you get what's called integer overflow. In other words, it actually wraps back around to the start of the range of values. And the reason this happens is really very trivial. 256 as a byte sequence looks like this. So 256 is really just 1 for the place value of 256, followed by 8 zeros. Now, when we cast this to a char, we're going to take the lowest, least significant 8 bits, which results in a value of 0. So yeah, so we have overflowed, resulting in truncation of our value. So it turns out that this was false. And this is an issue that plagued C programmers for a long time. As you can tell, this was unbelievably annoying, because even if I update my condition to say if condition is equal to 0, surely my C compiler is smart enough to realize that that condition is trivially false. Oh, and GCC, well, okay. Oh, right. Apparently, Microsoft's compiler is smart enough to realize. Oh, no, I'm sorry. No, I'm sorry. If we said not equal to 0, there we go, sorry. If our condition is not equal to 0, well, that still doesn't work. The compiler can't just inline that value. It can't realize that, hey, this is really just 256 not equal to 0. That's, you know, got to be true. Nope. Still has to perform this cast. And so in the most recent versions of the C standard, we sought to rectify this issue by introducing a header called stdbool.h. Stdbool gives us a few cool things. So in C, we have an additional type called _B bool. And you might say, oh no, that's terrible. Why is it written like that? And we'll get there. But now if I go ahead and I run this exact same code, I'm going to assign 256 to my Boolean and run this exact same condition now. And change this to condition bool. We go ahead and print this. Then what are we going to get? There we go. That's a little bit more like it. So what bool does, what the bool type does, is it performs this rule implicitly. And so if you assign a 0 to type bool in C, you're going to get a falsy value of 0. And if you assign a non-zero value to type bool, then you're going to get a 1, which is a truthy value. And now this is actually a really, really nice thing, because remember, 1 is within range of all of our integer types. It's literally a single bit to represent 0 and 1. And so we can cast this bool to whatever we want. I can say, you know what? Let's make this an unsigned char now. And guess what happens? Still true, because all we were doing is casting 1 to a char, which is still 1. It's truthy. And so we introduced a Boolean type in recent versions of C, and this is what it looks like. It's pretty neat. But we still have some issues. In Java, we really liked Booleans because, well, we didn't like Booleans because they were called Boolean. It was really long. And this is a little bit better, but it's ugly. And also, we still have no way to write true and false. right? We still have to stick with 0 and 1, which is a little cryptic. And so this header, stdbool.h, gives us a few things. It lets us, instead of typing underscore bool, to just type bool, like this, all lowercase, which you'll note is actually defined, and you can't see this, but it's defined to that Boolean type, and it gives us macros for true and false. And so I can instead just type true, and I can type false. Pretty neat. And so yeah, so that's how Booleans work in C. In general, nowadays, you should always use stdbool when you are working with Booleans in C. There is no reason to stick with the older convention anymore. It used to be a very, very useful thing for us to have, but nowadays, we don't really need it anymore. And so, because recent versions of the C standards provide us with this excellent feature, we are going to go ahead and use the Boolean type bool whenever we can to represent Booleans to avoid awkward issues like this one up here. All right, and that is the other types in C. Pretty straightforward, right? It's really quite simple. We've now completed, we've rounded out our types. We've now reached parity in C with the types that we know in Java. We now know about all of our ints, of which C has many more than Java. We know about the fixed width ints from stdint.h. We know about floats and doubles. And by the way, there's actually another type called long double in C. And it's really just, it's implementation defined. I've never seen anyone use it. 3, 5, 8, 9, 7, 9. Is that gonna overflow it? No, it's not. 3, 2, 6, 3, 2, 6, 3. Nope, still not gonna overflow. Okay, cool. So a long double, in theory, has a much larger range than a double. In practice, it depends on your compiler. So, you know, I recommend against using these if you really need a larger floating point value, then you can use a multi-precision arithmetic library like MPFR or GMP. But yeah, so we learned about floats, float double, long double. We've learned about the old way of doing Booleans with ints and why it kind of sucks. And now we've learned about the new fancy way of doing Booleans with a Boolean type and this header stdbool.h. Great. So now we know all of the types in C. Let's move on to something a little bit more fun. Let's learn about functions. So we're going to go ahead and start a new C program for this. Functions.c. There we go. We've got our nice program. Going to go ahead and add it to CMake. There we go. Reload our changes, and here we go. So now let's learn about how functions work in C. Functions in C are really quite simple. They work in basically the same way that you know them from Java. They really, really are not anything new here. So let's just, for some very basic practice, write a function that you've seen many times. We're going to write a function to take the average of two numbers. And we're going to have this function return an integer. And we're going to have it take two ints. And, you know, to indicate what value this function is going to return, I'm just going to write my expression. If we want to call this function, then we're going to call it in exactly the same way we did in Java. So if I want to take the average of 10 and 20, which should give me 15, then we can do that. And actually, I'll go ahead and write this out here just so we can see it a little bit better. But yeah, so we call it in exactly the same way we did in Java. We say average 10, 20. Great, and if we run the right program, then we will see that our average is 15, as we were expecting. And it's not much more complicated than this. It's really not. Yeah, functions in C work in exactly the same way as you think you do. You can nest these things too. So if I wanted to say, you know, I wanted a really roundabout way of getting 20, I could say average of 10 and 30. There we go. Done. If I want a function that, let's say, doesn't necessarily return a value, it just does some stuff and then doesn't return anything, I could just say void. And, you know, and a void function is not going to have a return value, and we can't use it, but it works the same way as a void in Java. It's going to execute some code, maybe modify some state, but not actually return a value. And BlueJay asks, so we don't have to declare the function. I mean, we do have to declare the function. We declare it right here. This is the declaration of the function. We declare it in line the same way that we declared functions in Java. Now, there is a caveat to this. There is a very important thing to note, and that is that in C, there is a strict ordering to your program. So, let's say that in Java, if I wanted to write this program like this instead, I could totally do that, right? I could just say, okay, I'm going to write my average function. I'm going to call it from main. The Java compiler is going to go, okay, cool. I just need some function average. When I get to that, I'm going to resolve it to this name and run this function. Cool. Let's see what happens in C. So I'm going to go ahead and compile my program now. Let's get rid of this other types binary. I'm now going to compile my functions program. And we see, oh, this is a problem. In function main, warning, implicit declaration of function average. Implicit declaration. What does that mean? Well, you know what? Hey. Oh, you can't see it. My apologies. There we go. Okay, so anyway, so when we compile this, we run our same compile command as normal. We get this warning, implicit declaration of function average. And what on earth does that mean? I mean, well, you know what? It might be just some weird pedantic thing. Our program compiled, let's run it. And we get a value of 15, which is what we were expecting, which is somewhat interesting. But this warning can actually cause us lots of problems, and it can start to cause us more problems with more complicated programs. What this warning means, implicit declaration of function average, is that when your C compiler saw a call to that function, so in other words, when it saw our call to average on line 5 of our program, it hadn't yet encountered this function. And so it had to wait to get the definition of this function before it could resolve it. This is a big no-no. This can actually cause our programs to not compile. And by the way, just to give you an example of what happens if we try and call a function that doesn't exist in C, just so you know what the compiler warning looks like, then we're going to get something like this. It's going to tell us implicit declaration of function average, and then we're going to get this kind of confusing message down here. So user bin LD in function main, undefined reference to average. So what this means is that your compiler attempted to output a call to a function called average. And the compiler can actually do that, and there are reasons why this might even happen sometimes. The problem, though, is that when our linker, another program in our compiler toolchain that we'll talk about at a later date, looked for that function average, looked for a definition, and said, hey, I can't find it. I cannot find your function average, so I cannot link your program. I cannot make an executable that can run. And so to avoid all of these different types of issues in C, when we write a function, we have to make sure that the declaration of that function comes before any references to it. And now, as BlueJay said, there are times where potentially we may need to call this function before its declaration, or before its definition. We might want to declare this function before we define it. You know, if average is written in another file, we may need to call this function average before the compiler has actually found its definition. So I'm going to go ahead and actually put average back down here. And that's so we can learn about something in C called forward declarations. A forward declaration in C is basically you giving a hint to the compiler. You're telling the compiler, hey, I know that you have not seen a function called average yet, but you will. And this is what it looks like. So you're telling your compiler, hey, I am going to write this function. I'm going to write a function called average that takes 2 integer parameters. But we haven't done that yet. So just a hint, whenever you see a function called average, it's going to have this prototype. It's going to have this structure. It's going to return an int, take 2 int parameters. And whenever the compiler gets to your function, it's going to look at your function definition and say, ah, yes, I remember this function. You told me I was going to find that. Let's call it. And so now if I go back and I try and compile this program with our forward declaration, but our function down here at the bottom, let's see what happens. Go ahead and switch back to our terminal. And the warning went away. Why did the warning go away? Well, because we now haven't violated any fundamental assumptions that the compiler makes. We defined our function, and when the compiler saw this call, it knew what that function was. And so, hey, it worked. And so yeah, so this is the concept of a forward declaration. And now when we're writing code within a file, I encourage you to actually not do this. I highly encourage you to just go ahead and put your functions in order. So within a file, average might come before main. Say, hey, when you see a call to average, we already know what it is. But when we start talking about header files later, these scary .h files that we've seen, these are going to become important. So just a preview of how forward declarations work. And we'll go ahead and actually just leave this in here so that you can see it. Because now I am going to show you one more thing that differs between C and Java. Remember that in Java, there's a lot of what we might call magic that happens. There are a lot of things that we might do in Java that the compiler might assume we wanted to do that we actually didn't tell it to do. One of these things is if, let's say that we actually want to factor our average function out a little bit. Let's say that, you know, hey, I want to do this in a slightly simpler way. I'm going to say, okay, so int sum, I'm going to have 2 integers called sum and one called retval, let's say. Sum is going to be assigned the value a plus b. Retval is going to be assigned sum divided by 2. And before we actually return our average, what I want to do is I want to say, okay, I'm just going to print my output. I'm going to say we called average with 2 parameters. And that's equal to our sum divided by 2 is our average. Pass in my values. And this is really the same function from before, right? It's doing the same thing. It's also just going to print some stuff. And yeah, there we go. Hey, average 1030, average 1020. Great. This is exactly what we were expecting. And I'm actually going to make this a little bit simpler for us, just so that it's easier to read the output. All right. So average of 10 and 20, 30 divided by 2 is 15. Cool. Just what we were expecting. Now you're probably like, hey, Andrew, I know how to program. Stop showing me how functions work. And you kind of have a point. But let me show you something a little bit interesting about C. So in Java, and y'all can type this in the chat. I actually just want to see whether or not Java programmers are aware of this. If I didn't assign a value, let's say I never assigned a value to sum at all, what value would sum have? You can just type it in the chat if anyone knows. 0! Yeah, exactly. Yeah, Prince Logic and Blue Jay got it at really about the same time. Yeah, so it's going to have a value of 0. And so going into C, you might be like, hey, you know what? I've got this. I know what's going to happen. If I don't assign sum a value, it's going to be 0. Let's validate that assumption. Oh, I can't do this in the Visual Studio compiler. Let me switch over to the other one. Okay, so let's say that I am gonna compile this under Unix. Oops. Sorry, wrong window. Switch OBS scenes and not lines of a command line. Oh. Huh. That's not 0. That's like really not 0. That's insanely not 0. So yeah, what on earth happened there? And oh no, it looks like we've got some spam. Yeah. I'm just gonna ignore it. I'll figure out how to ban people from chat by tomorrow. Sorry about the disruption, guys. Anyway, XISZ says you get the address. And that's kind of a good intuition, but it turns out to not be quite how it works. And maybe we can elucidate this a little bit more if I do something like this, where I'm just going to go ahead and print the values of all our variables going into the function, and then print our assignments, and then going out of the function. And so now if we switch back, we're doing lots of screen switching today. I should buy a Stream Deck. Well, see, okay, cool. This is kind of, well, okay. So by default, it looks like our sum had this value, and our average had this value. Okay, we can, what if we just run it again? Oh no, that ain't right. Now it's negative. Okay. Oh, it's negative again. Oh no, what's happening? Wow, what a strange behavior. Now, I want to show you what happens if we call this function twice. Now, I'm going to call this function with the exact same parameters. Literally exactly the same parameters. We're going to be doing exactly the same thing twice. And so you know how functions work, right? If we run the same function twice and that function has no side effects, it has no external state modifications, then it should do the exact same thing and we should get the exact same values. So now I'm just going to go ahead and clear the screen, recompile our code. Huh. Oh, wow. That's interesting. Okay, so our first time we got gobbledygook values going into the function, and we got our correct values going out. The second time when we went into the function, before we even defined our average and our sum, they had the correct values. So clearly what we have learned from this is that your computer is actually omniscient. Your computer knows really exactly what you want to do, and it can actually predict what you're trying to do before you even do it. So even before you say, hey, the sum of 10 and 20 is 30, your computer goes, hey, I know the sum of 10 and 20, it's 30, this is what you're trying to do, here's your value, done, I did it for you. Aren't you happy with me? I'm so smart. And that is a lie. Computers are very smart, but they're not quite that smart. They can't read into the future. What's happening here is something that relates a little bit to, if you remember when we talked about recursion in Java, we talked about the concept of stack frames. So let's talk about stack frames a little bit, or let's just talk about the call stack. So the call stack. Okay, so just to review how the call stack works is that on the call stack, every function is assigned a little bit of stack space. Stack space being essentially just some space on this internal computer data structure, this region of memory that we call the stack. And so when our program starts off, now we're going to see something new here, and that is that, well, let me just do it. So we're going to start off our program with our main function being on the stack, right? That's the very first thing we're going to see on the stack. I'm going to draw main in blue. Here's our main function. So this is what we call main's stack frame. Every function gets one stack frame. And what a stack frame is it's a little bit of memory that contains all of the state that is necessary to run our function. And so if we very briefly go back and look at our code, we'll see, okay, what would we expect to be on main's stack frame? Well, we would expect to see a variable, right? This variable, function value. Okay, cool. So let's go ahead and put that on the stack. So let's switch back here to our stack drawing. And now main's stack frame is going to look like this. We're going to have somewhere in memory that int. Our local variable. It's got to go somewhere, so it's going to go on the stack. However, that's not the only thing that's on the stack. There are actually some other things that your computer puts on the stack. And the most notable one, for most functions, is what's called the, or at least on the x86 architecture, and we're not going to talk about what this means right now. You'll get to it in a computer architecture course, or we'll get to it when we talk about assembly. But we will have the frame base pointer saved. So in other words, this is what we call the EBP save. And again, you do not need to know what this means for now. You can just go, wow, those are some interesting symbols, and move on with life, and you don't really need to know anything past that. But now let's see what happens next. So when we try and assign a value to fn val, what actually happens? Well, what happens is we create a new stack frame for our new function that we're calling, which I'll draw in red. And so this is going to be the stack frame for int average. And average takes 2 ints. All right, cool. So knowing our stack frame layout that we talked about before, we can figure out what our stack frame for average might look like. Average contains the following things. It's again going to have a base pointer save. Well, actually, it's going to have something else too. It's first going to have a return address, which you don't really need to know about for now. It's going to have a base pointer save, which again, you can ignore. But after that comes our two variables, our two local variables. We had an integer called sum, and we had an integer called retval. And I'll note, you don't need to know what order these things come in. It's compiler dependent, and it's architecture dependent, and it's ABI dependent. You really don't need to know what order these variables are on the stack. You just need to know that they're there. And so this whole thing here is average's stack frame. So when we call main, a stack frame is created for average and pushed onto the stack. Systems engineers draw the stack growing downwards. Again, we draw the stack growing downwards, not upwards here. And you'll see this in your computer architecture class. The stack grows down now. And so yeah, so we're going to push a stack frame onto the stack. And we're going to have these integers. Now, these integers, by default, remember, are really just sequences of 4 bytes in memory. That's all they are. And so when we ran our program and we saw some absolute garbage for those values, before we assigned something to them, what we were really seeing is we were seeing the values that lived at these memory addresses before that call to our function. And so when we call average the first time, we start off with just some junk in here because that's what lived at those addresses last. However, once we actually run our function, we assign some values, right? Sum becomes a plus b, retval becomes sum divided by 2. And so we've assigned some values to those positions in memory, and that's now what lives at those positions in memory. And so we now have some values. This is a plus b. Oh, if I can write. And let me zoom in on this just a little bit so we can see it better. And our return value is going to be sum, whoops, is going to be sum divided by 2. Now, after this function returns, its stack frame is going to be popped off and removed. And so as a result, this stack frame is just going to go away completely. All right, we're no longer going to have a stack frame for average at that point, we're just going to have main stack frame on the stack. However, remember that main now is going to call average again. And so it's going to call average again. And so we're going to recreate this stack frame for average. And because the stack grows downwards and because our stack frames in C are a fixed size, the stack frame for the second call to average is going to have the exact same layout as the stack frame for the first call to average. As a result, when we try and read these uninitialized values, they still have, or these uninitialized addresses, these uninitialized positions in memory, they have the same value that they did before, and that is why when we run our program, more specifically when we run our program in GCC, we get the same value at those positions in the stack frame. So yeah, that is one brief caveat of how functions work in C. Is stack frame reuse is something that occurs. And remember that stack frame reuse was the cool thing about recursion. That's why we liked recursion, because we could reuse stack frames. We could reuse positions in memory implicitly. That was a great feature and facility to have. But C in general maintains its commitment to having a little bit less magic by default than Java. And so in C, if you want to ensure that you don't get garbage values for variables, you must always initialize them first. Blue Jay, if we were to set up garbage collection, we could prevent the ghost number thing. Well, stack frame reuse would still occur. You may get stack frame clearing like you do in Java. So in Java, when you say int sum, what Java does is it says, I'm going to allocate space on the stack for an integer called sum, and I'm also going to assign it the value 0. C only does that first part. It only says I'm going to allocate the value, and not I'm going to assign something to it. So it's not an artifact of garbage collection, it's more just an artifact of a built-in Java behavior that C doesn't exhibit. And so here we see we've initialized both sum and retval to 0. So now if we go back and we run our program, we recompile and rerun. There we go, let's do that, and run it. Our garbage is gone. We get the same things that we would expect. And now, to be honest, this is a crappy way to write this function. You know, I really could just write int sum equals a plus b, int retval equals sum divided by 2, and that would probably be a better way to write this. But this was just an example to show you how stack frame reuse can affect your programs, and why we always want to assign values to variables in C. So, that being said, let's talk about why we might want to always assign values. And now we are going to begin, and we're not going to cover everything about this today, because this is a very challenging topic that people can struggle with sometimes. We are going to move on to talking about probably the scariest part of C for a lot of people. And that is, we are going to begin talking about the lovely, lovely, lovely things in C that we call pointers. So, yay, pointers. All right, now, we are going to talk about pointers. Pointers, again, are something that people are very scared of. However, I also think that a lot of that fear is relatively unfounded. And I don't just say that because I'm a pretentious snob who does lots of system stuff and knows how pointers work. I say that because the fundamental concept is fundamentally very, very, very simple. So in C, remember that we can write declarations. We declare that data is going to live in a position in memory. All C really does is it's a language for manipulating values. It's a language for manipulating values in memory. That's all C really is. And it does some fun stuff with the processor, but for the most part, C is used to manipulate values in memory. In fact, for a large part, that is what computers are used for, is manipulating values in memory. And so when we talk about pointers, we are going to rely on a fundamental assumption about the C abstract machine. And that fundamental assumption about the C abstract machine is, in C, and here we'll go ahead and give this a red star to indicate this is important. In C, every value has a memory address. All right, so what does this mean? That means that every single bit of state, every single bit of data that we manipulate in C has a memory address. If we switch back to this program, that means that sum has a memory address, retval has a memory address, funval has a memory address. In fact, even the function average has a memory address. Main has a memory address. And so yeah, every value in C, every named value, every variable, and really just anything that we can manipulate has an address. This is not necessarily true of your computer. When we talk about how assembly works, if I ever do an assembly stream, or once you get to your computer architecture class, you'll learn that actually some things don't live in main memory. They might live in cache, they might live in registers, but the C abstract machine says every value has a memory address. And so, following from this, we can define a pointer extremely simply. A pointer is the memory address at which a value lives. So a pointer is the memory address at which a value lives. Now, if there is one thing I want you to take away from this entire series, it is that a pointer is the memory address at which a value lives. This is how we define pointers. This is the fundamental concept behind a pointer. And a pointer is fundamentally not really any more complicated than this. It's just a memory address at which a value lives. So, in C, if I write something like, let's say I'm going to get myself some memory. So let's say that this is going to be memory. Memory is just going to be some big, long array. The most fundamental abstraction of memory is really just a big, long array of values. Is that really an authentic statement of how memory works? No, but it's very, very useful when we're talking about pointers. So we're going to pretend like memory is this big array of values. And when I say in C something like int sum, what I'm doing is I'm telling the compiler that I want to allocate 4 bytes. And so if this is memory address 0, I'm saying that I want to allocate 4 bytes to fit this value called sum. And we have a question from Blue Jay. Does this have to do with pass by value? We will talk about that. That's definitely something that we want to talk about with regards to pointers. But anyway, so let's say that I write int sum, and actually I'm going to write int sum equals 20. So what I'm doing here is I am telling the C abstract machine that I want to assign the value 20 to the 4 bytes in memory at which sum lives. So sum equals, 20, not 0, 20. So sum equals 20. I can do this for other things too. I can say, okay, average, int average, and if I space my words correctly, int average equals sum divided by 2. What I'm really doing is I'm again telling the C compiler, hey, I want some space for an integer-sized variable of 4 bytes called average, and I want to assign a certain value, in this case 10. And this is really, at the most basic level, again, how memory works. So now let's talk about pointers in C. A pointer in C looks like this. And now this is going to be a new little bit of notation that we haven't seen before, but it's not really that scary. We are going to say int star sum pointer equals the address of sum. Okay, so this is a little complicated. So let's follow this step by step. The first thing that we see here is this notation int star. What star in C means is that this variable is a pointer type. So this variable represents the memory address at which a value lives. We can read this type as follows. Some people can really struggle to read pointer types in C. They can be a little bit challenging to read. But we can read this declaration here, int star, as pointer to an int. So anytime you see a star, that means pointer to something. So int star sum pointer means we have a variable called sum pointer called, that variable is a pointer to an int, right? So star pointer to. That's how we're going to read that on the left side of an expression. So anytime we see type name star, pointer to type name. Int star, pointer to int. Double star, pointer to double. Char star, pointer to char. So yeah, that's how that type declaration works. And now this thing here that we call the ampersand, I have seen more terrible, awful explanations of pointers that just confuse the bejesus out of people on how you should read this character. People have these awful ways of telling you to read this character, and I'm going to tell you that the absolute simplest way to read this character is every time in C you see an ampersand, without fail, every single time you see an ampersand in C, we are going to read that ampersand using the words address of. And there's a really easy mnemonic for this, because you'll note that A, address, is the first letter in the word and, which is how we read an ampersand. Oh, and Prince Logic has a good question. Does it matter where the asterisk is located? It doesn't. It actually doesn't matter. You could bind the asterisk to the type name, or you could bind it to the variable name. And I'm going to show you why you should prefer my way of doing it, of binding the asterisk to the variable name instead of the type name. So in other words, putting the space in between. And I'm even going to highlight that there's a space here. Putting the space in between the type name and the star instead of between the star and the variable name. We'll get to that in a second. And it has to do with a really weird quirk of C's grammar. So, but it actually does not matter. No, at a fundamental level, it doesn't matter. And so let's figure out how this line of code is going to execute. Pointer to int sum pointer equals the address of sum. Well, just from that plain English, you can actually probably figure out most of what's going on here, right? This kind of plain English way of reading things makes this process pretty simple. We said, okay, we're going to allocate space for a pointer in memory, which I am just going to preemptively assume that a pointer on our system is 8 bytes long. This is common for 64-bit systems, which is what you're all using. So we're going to assume that a pointer is 8 bytes today. All we're doing is we're saying sum pointer is just the memory address at which a value lives. And that value happens to be sum. So when we see ampersand sum, address of sum, we're going to get the address at which sum lives in memory. Where does sum live? Address 0. And so sum pointer here has a value of 0. And so yeah, so the value of some pointer here is 0. And we'll note that here. That's relatively straightforward. Right? Again, we've got a plain English declaration. Some pointer, pointer to int some pointer equals the address of sum. Very straightforward. And if we know how memory works, and if we run with this abstraction of memory just being this sequential array of values, then it's relatively straightforward. Okay, awesome. Let's now do something that's a little bit more fun. Yeah, Tuna actually just predicted exactly what we're going to do. I am going to declare a pointer to a pointer. And so I'm going to declare this variable now. Int star star, I'm just going to call this d pointer, equals the address of, and here we'll write it in red just to make these symbols stand out again, some pointer. Okay, so what's going on with this? So this gives us a fundamental property of our readings, so of how we read these types. And it's just another kind of brief shorthand of how we read pointer types in C. So these stars, each star, remember, means pointer to. And so if we see int star star, what does that mean? Pointer to, pointer to, int. Right, and again, this makes sense, right? Some pointer, the thing we took the address of, so the thing we took the address of is a pointer. And so as a result, when we take the address of something, we get a pointer to that type. So when we take the address of a pointer to an int, we get a pointer to an int. Great, so now in order to actually evaluate this code, we know that it's going to be, it's going to be 8 bytes long. So we're going to say ending address is 24, and d pointer is going to be assigned the address of some pointer. Well, what's the address of some pointer? Someone in chat, go ahead and you can say, what's the address of some pointer here? Let's see here. Blue Jay got it. XISZ, that's not quite correct. It's not 16. That's the address of d pointer. The address of some pointer is 8. So yeah, when we say address of, we mean the address at which that value starts. The address of the first byte of that value. Yeah, not the last value. It's the address of the first byte of that value. Okay, great. So now that we've gotten that kind of clarified, let's talk about one more thing that we can do with pointers in C. It's all well and good to be able to get the address of things, but what are we gonna do with that? Right? Like, what are we actually gonna do with that value now that we have it? It's like, okay, cool, great. We've got a 0, and we've got a 16. That's pretty sick, but like, why? And the reason that we like this is something that I am going to demonstrate for you now. So we're going to write another function. Yay, we like these. We're going to write a function to do something that you may have tried to do in Java and got really, really, really frustrated by. And that is, I am going to swap two values. So, in Java, when we wanted to swap two values, you probably tried something like this. So let's say that I have two variables. I've got two variables in main. We'll get rid of our for declaration. One of these variables will be called int a. It'll have a value of 7. And we'll have int b, which will have a value of 43. And I just want to swap these two values. That's all I want to do. So what I am expecting at the end of this is that a will be equal to 43 and b will be equal to 7. And let's just go ahead and we'll do a quick printf here just to show what these values are now. All right, and in Java, here's how we swap values, and it's how we're going to swap values in C too. We have to create a temporary variable to store one of the values. We copy the other value to that variable that we just stored. Oh, I did that wrong. There we go. And then we assign something like a equals b to copy the other value. More specifically, we assign, sorry, a equals temp. There we go. It's nice when we can write basic code. And so, if I'm just going to go ahead now, and I'm just going to print, just to make sure that things work, I'm going to print it in swap. And I'm also going to print it in main. All right, so what we're expecting is that we're going to see that these variables swapped, and we're going to see it in main, and we're all good to go. Oh, okay. Well, that's unfortunate. So we can see that in swap, the swap that we were expecting happened, but when we come back to main, it didn't. So what on earth is up with that? Well, this has to do with the fact that variables in C, Prince logic got it, are universally passed by value. So everything in C is passed by value. You'll remember in Java that you probably tried to do something like this. You probably tried to assign, you know, some variable. You tried to do something like this, where we tried to assign to a parameter, an integer parameter in Java, and we saw that it was reflected in the function, but it wasn't reflected outside of our function. My students who did the recursion assignment, almost all of you probably did this at least once. So, you know, yeah, it's a common error. And in Java, we had to do this dumb thing when we wanted to actually manipulate these. What we had to do is we had to say, okay, I'm gonna wrap each of these in an integer, in an array now. And C is yelling at me, we're gonna talk about arrays tomorrow. And then you had to manipulate the 0th indices in these arrays. And that worked. But a lot of you, when I told you to do this in office hours, you looked at me and you said, or you looked at maybe our professor when he mentioned this in class, and you said, that's the dumbest thing I've ever heard of. Why do we have to do that? Well, it's because Java basic types are primitive types. Ints, doubles, floats, chars, booleans, we're all passed by value. The same thing happens in C, but we can circumvent this. We can get a little bit sneaky and say that instead of taking integer parameters, I am going to take integer pointers as parameters. And what I'm going to do to swap these values is I'm going to assign now the values that live at these memory addresses, not the values themselves. So I'm going to say that temp is equal to the value of B. The value of B is equal to the value of A, and the value of A is equal to temp. Now let's talk about what this means. I just essentially decorated this function like a Christmas tree. I covered it in stars. These stars up here mean the same thing that we talked about earlier. It just means pointer to int. And that's what they mean in type declarations. However, when we see them in line like this, what this operator means, prefix asterisk in C. So let's say that I am going to now say int sum val equals the value at sum pointer. Now, let's remember, let's say this again. A pointer in C is nothing but the memory address at which a value lives. And if I could get fancier, like, firework effects for this, I would. But for now, you'll have to stick with my crappy rectangles. But a pointer is nothing but the memory address at which a value lives. And so when I perform this operation, this asterisk really just means, and you can read it as value at. And so what we're doing is we're saying I want to get the value at this memory address. I want to get the value at the memory address that lives inside some pointer. And so what this really converts to here, star some pointer can be read as the value at the memory address represented by, or the address stored in, some pointer, or in other words, the value at address 0. And so in order to evaluate the statement, what we're going to do, and what your processor does, is it's going to say, okay, cool. I'm going to figure out, well, what lives at address 0? Let's go to memory, and let's look it up. Well, what lives at address 0? Aha! It's this value sum, which has a value of 20. And so as a result, the value of sum val is now going to be 20. The same value that sum had. Great. Now, this operation, taking the value at a memory address in C and really in all programming languages that support pointer semantics, is called dereferencing. So, saying the value at is the same as saying a dereference. And this is a word that you're going to hear a lot said by C programmers. That's what we call this operator. This prefix star is the dereference operator. But you can read it as value at memory address. So we say star some pointer, value at some pointer. And now just to show you one more thing, what we can do is we can actually assign values to pointers. And so let's see an example of that. And the example that we have is this program. So let's read this as simply as we can. Int temp is equal to the value at address B. So B is a memory address, so all we're doing is we're getting the value at that address in memory. And now what this scary line with 2 stars does, remember, if you read prefix asterisk is value at, all it says is the value at address B is equal to the value at address A. Right? So we're assigning to address B. So we're assigning to the range of memory denoted by address B, the range of memory that's an integer wide at address A. So value at B is equal to value at A. Then all we're doing here is we're saying the value at A is equal to the value temp. Right? Relatively straightforward. So again, and we'll even write out how you can read this line, because this one is a little bit scary, right? This one is value at address B is assigned value at address A. Awesome. So now let's go ahead and run this program. Let's go ahead and compile it under GCC, because it seems like Visual Studio has decided that it doesn't necessarily like when I do weird things with code, which is fine. Let's go ahead and recompile this. Oh, and we did forget to change something. So what happened is, okay, fine, we forgot to change A and B. A and B are of type int. And so what we're really doing is, remember, a pointer is just the memory address at which a value lives. A pointer is an integer. All pointers are integers that denote memory addresses. And so if we try and pass A to this function swap, well, what we're really doing is we're trying to pass memory address 7 to that function. And you know what? Yeah, why don't we try it? Why not? This could be fun, potentially. Let's go ahead and just run this program. Let's go ahead and say /functions and segmentation fault. All right, this is our first seg fault. Welcome to the world of C. Remember how in Java I said that we got exceptions and they were super fancy? They told us when we tried to do things that were forbidden, and they gave us nice error messages and backtraces, and they were super duper helpful for debugging, and they were great. We loved them. C does not have exceptions. C, you either handle errors yourself, or your operating system will tell you when you do something wrong. This is an example of that. This is not a message that we printed in our program, right? Nowhere in this program do I have printf or putS segmentation fault. This is the operating system telling you, hey, you tried to access an address that you do not have access to. Your program, every program, when it runs on your computer, is allocated an address space by your operating system. So remember that we said that earlier, that kind of linear sequential view of memory was really a pretty big abstraction. Now let's go ahead and redraw memory. So this is memory v2, now with multiple applications. So this is memory again. And now I'm going to draw it as this big kind of block. And again, terrible abstraction, but we're going to go with it. Now, each little area in this block belongs to a different program. So let's say that some of this memory, let's say that all the high memory, because that's how Linux works, is assigned to the Linux kernel. So this memory is owned, whoa, hello. This memory is owned by the Linux kernel. The kernel is just the very fundamental part of your operating system that deals with things like interfacing with devices and multitasking and multi-user handling and stuff like that. And let's say that we have some other applications running. Let's say that, I've got my shell running currently. And so this is ZSH is the shell that I use. Let's say that we've got a little bit of memory that might be occupied by, oh, I don't know. Let's say that, I'm currently streaming. So we've got some memory occupied by OBS. And I use Firefox, so the memory usage isn't quite this bad, but let's say that, you probably use Chrome, and so Chrome is just going to eat up all of your memory because Chrome is a memory-hogging demon. And what your operating system does is it maintains something called segmentation. And what segmentation says is that each process is not allowed to access anything that is outside of its address space. And so these red lines represent segmentation. And let me tell you why segmentation is important. So Chrome maintains all kinds of stuff in memory. Let's say that you've got a web page open. Let's say you've got YouTube open. Chrome is maintaining a ridiculous amount of state because it's Chrome. You've got an instance of the V8 JavaScript interpreter that's running and a whole bunch of JavaScript values. You've got the video itself that's playing is taking up a large amount of memory, and the code that's necessary to buffer that video and render that video and all that kind of ridiculous stuff. And all kinds of things. The document object model, your actual document itself, just all kinds of just stuff in memory. Now let's say that I am the author of a malicious program. So, I am the author of a malicious program. And so I am writing a virus. And what my virus is going to do... Nuben, we actually don't know that memory address is the kernel. I don't remember exactly how where Windows places kernel memory. I think it places it in a high memory. But I might be wrong, so you can actually correct me on that if you know Win32 or WinNT internals. I don't. But anyway, so yeah, let's say that I'm writing a virus. It's not something that I do in real life, but let's say that I'm doing it. And what I want to do is I want to get at some stuff in Chrome. So let's say that, you don't just watch videos in Chrome, you do other things too. Let's say that you do your banking in Chrome. I do my banking online. Everyone does their banking online nowadays. So let's say that my virus is just kind of sitting in memory, it's chilling, and what it's doing is it's waiting. It's just waiting very, very, very patiently for you to attempt to access your bank's login page. And what this virus is doing is it's just constantly scanning Chrome's memory, and it's saying, can I find in memory a signature that looks like a password field? And so what it's doing is it's saying, okay, I'm just going to wait, I'm going to wait, I'm going to wait. Oh my gosh, you accessed your bank's page. Cool. Now I'm going to start attenuating on that region of memory. I'm going to say, okay, cool. I'm going to start scanning just this little region of memory. That's your bank's page. And I'm looking for passwords. And there it is. I found a password. So now what my virus is going to do is it's going to say, awesome, give me your password. I'm going to read that address in memory. I'm going to read that address in memory. I'm going to get your password. And now what I'm going to do, because I write viruses and I'm an unscrupulous person, is I'm going to copy your password, send it off to a remote server somewhere, and now I have your password. Cool. That was easy. It was super easy, right? I got your password. Done. It only took a few minutes. It's not even really that hard of code to write. Well, there's actually a nice little bit of protection that your operating system builds in, and that is that if your program attempts to access memory that is outside its address space, your operating system is going to say, absolutely not, you cannot do that. Your operating system is going to say, you don't have access to that memory, that's not yours, go away. And what your operating system is going to do is, computers are pretty metal, so what your operating system is going to do is it's going to realize that what it did, and the punishment on at least Linux for accessing memory that's not yours is execution. And by execution, I mean death. The Linux kernel is going to go in and it's going to kill your process. So, if in the real world, we're assuming that there are no security vulnerabilities, my virus tried to access Chrome's memory to say, hey, give me your password, the Linux kernel would say, absolutely not, you cannot do that. You violated my memory segmentation. And as a result, you are going to get something called a segmentation fault. And now I will note, you oftentimes hear these referred to as seg faults, just for short. That's the term that I'm going to use. Seg fault. It's not French. There we go. Seg fault. This is going to be the most common type of error you see in C, almost definitely, because anytime you try and deal with a pointer incorrectly and try and access something that's not yours, anytime you have a null pointer, anything like that, you're probably going to get a segmentation fault. And so when we tried to run our program, so if we look at our output here, we got a seg fault. We tried to access memory address 7. And actually what I can do is I can print the memory addresses inside of swap that we're dealing with. So what I'm going to do is I'm just going to say printf A is at, oh, I need to have some way to differentiate this from the actual values. So I'm just going to say, let's see here. This is going to be star A, star B. So A is a pointer, which is denoted with the printf code %p. B is also a pointer. All right, and now let's go ahead and recompile this program and look at what memory addresses these values live at. So let's go ahead and recompile. Still get a warning, whatever, that's fine. Aha, right. A is at address 7, and B is at address 43, which in hexadecimal is 2B. So what we need to do is we need to go back to our program, and we need to refactor it. And we need to say that instead of passing the values of A and B, I want to pass the addresses at which A and B live in memory. I'm going to turn my ints into int pointers. I'm going to take their addresses. So now what I'm saying is I want to swap the address of A, the address of B. And then swap is going to dereference these pointers to actually change their values. So now, if we go ahead and we switch back to our console and we recompile this program, the first thing we'll note is that, hey, the error was gone. And actually, let me go ahead and clear this. We'll go ahead and do this. And now if we run our program, we see that we now got the correct behavior. You'll note A is now 43 and B is now 7. To highlight the change, let's just go ahead and print the initial values before swap, just so that you can see that things happened. Recompile, rerun. So there you go. We started off with A equals 7, B equals 43. These are the memory addresses at which A and B live. Now remember that address space doesn't necessarily start at 0. That's just, again, an abstraction that we were using to make me not have to do much mental math, because I'm not very good at it. And now within swap, we changed the values that live at those memory addresses. And now when we come back to main, we can see that they have changed. This is a really, really, really powerful feature of C. It's an extremely useful feature that we're going to be using a lot in the days going forwards. You're going to see pointers an incredible amount going forward. And so I would highly recommend that maybe before we move on to the next lesson, if you're really following along with us and you're really trying to, kind of stick with the program that we're going with, review the notes from today and make sure that you are intimately familiar with how we read this notation, where ampersand reads address of, star prefix reads value at, and type star means pointer to type. And that is pretty much the only thing that you need to know about pointers in C. So, just to get some feedback in the chat, why don't y'all go ahead and let me know, how are you feeling about pointers right now? How does all of this sound? It's a relatively simple concept, but do you think that you've got a pretty reasonable grasp of at least the basic concepts? And hopefully we do. And I'll let y'all... Oh, Prince Logic, you've worked with him for a while, but now you truly understand it. Good. I'm glad I was able to make these make sense. Again, I think that a large portion of why pointers are scary to people is that people make them harder than they need to be, right? Again, the number of just terrible, terrible, terrible explanations of pointers that I have heard is through the roof. You may be familiar with, there's this video of where people are playing with these LED things and they use that to explain how pointers work. And that's how I learned pointers. And I was like, this is terrible. And so, yeah, so this is really all you need to know about pointers. This is the fundamental concept. There are some additional semantics that we're going to work with, and, we're going to have to play with certain things to make sure that we really, really've got it. But this is the basic concept. And yeah, BlueJ and XISZ, yeah, I'm glad that this was helpful in strengthening your understanding of pointers. So yeah, this is pointers. All a pointer is an integer. It's a memory address at which a value lives in memory. And we can read this notation in C. Ampersand means address of, star means value at, type star means pointer to type, and that is it. So yeah, that's pointers. Now tomorrow we're going to talk about applications of pointers, and we're going to talk about how pointers start to get interesting, and some fun things that we can do with pointers. But for now, I'm just going to leave you with one more example of how we might want to use pointers just to give us a little bit more practice. So, I'm going to switch back to CLion real quick, and I'm going to write one more very simple function. Actually, we're going to write two functions. I'm going to write a function called pre-increment and a function called post-increment. Pre-increment is going to perform this operation, and post-increment is going to perform this operation. So in other words, we are now essentially re-implementing the unary increment operators in C. And what you'll remember is that when we type the plus plus first, what we are going to do is we are going to increment the value of the variable and return that same value. Right, so we're going to return that same value out of the function. We're going to return the incremented value. So the way we're going to write this is we're going to say star val, the value at val. That's a terrible name, but we're going to go with it. And we're just going to increment that by 1. So you'll note that we can use all of our special operators here with an address, or with a pointer dereference on the left side. So we say the value at this variable val is going to be incremented by 1. And then I'm going to return the new value of val. And we can do the same thing with post increment. So now what I'm going to do is I'm going to say, all right, now post increment. What post increment does is it increments the value, but it returns the original value. And this is something that trips a lot of people up. So post increment is going to increment the value that lives at this address, but the value that it returns is not going to be the new value. It's going to be the old value. So I'm going to stash that value away. So old val equals the value at val. I'm going to increment the value at val again. We've got to increment our variable. And then I'm going to return the old value. Okay, great. Let's test it. Pretty simple, pretty straightforward. We're really just re-implementing features of C that already exist, but hey, this can be useful to do sometimes. And so now, let's go ahead and try it. So, I'm going to try pre-increment on, let's say A. Let's say we're going to pre-increment A. And now I'm going to get rid of this call to swap, just because we don't want to mess anything up. And we'll keep this first call to printf, actually. And so what I'm going to do is I'm going to say, so pre-increment. And now pre-increment, we're going to print out the initial value, the return value, and the new value at A. So what I'm going to do is I'm going to print A. I'm going to print pre-increment A. Pre-increment, remember, address of A. We've got to pass a pointer to A, so we need to take A's address. And then I'm going to print the new value of A. All right, and now let's watch and see what happens when we run this. What we're expecting to see is we're expecting to see 7 and then 8, right? Because pre-increment returns the new value and then 8 again. And hi, Luscat, how's it going? How's it going? All right, so now when we run this program, let's see what we get. Oh, what on earth? So we get 8, 8, and 7? Our original value? What is going on with this? Why? What's happening now? What magic random stuff is C doing? So, this is another discrepancy between C and Java, and it's a very, very pernicious one. It's one that trips a lot of people up. It trips myself up very frequently. It trips... Most C programmers I know mess this up at one point or another. So, in Java, method parameters are evaluated left to right. In C, function parameters are usually evaluated right to left. XIS said last A just used the main variable. Right, yeah. A's value here was 7. Yeah, you're right. It used the initial value. And why is that? Because our function parameters are evaluated right to left. And so, as a result, we evaluated this A first and got 7. Now let me pull up our output so that we can see that. We evaluated this A first and got 7. Then we called pre-increment and we got 8. And then we printed the new value of A. We then evaluated A and got 8. Yeah, kind of crazy, right? Kind of crazy. And Prince Logic, why is that? That's a really good question, and I'm not gonna lie, I don't know. I really don't know why the implementers of our modern C compilers did this. This wasn't always the case. There used to be a lot of compilers that did it left to right, the way you would think. But no, it seems like nowadays most compilers are doing right to left. It seems like, yeah, the Visual Studio compiler is doing it. Also, I believe GCC is going to do the same thing. So if I go in here and I run my C compiler, by the way, being GCC, and I run this, then you see the same thing. So yeah, arguments are evaluated right to left. So what this means is, in C, you should almost never, and I'm gonna just repeat the almost, you can do it, but you should almost never, ever put a function call that uses a pointer to a variable that you are passing somewhere else in the function call inside the call itself. And why is that? Because right to left evaluation is unbelievably unintuitive. And let's get, yes, the order of evaluation is actually undefined. It's worse than this. It's not defined by the standard to be right to left. That's what, by convention, our compilers are using. MSVC and GCC, the two big C compilers, and Clang, the third big C compiler, all do this. But yeah, it's actually undefined by the C standard. And so manipulating a pointer inside a function call is another example of that magic phrase, undefined behavior. We don't know what's going to happen. It's not defined. We can read our compiler's documentation and it might say what happens on this compiler, but then we could switch compilers and who knows what's going to happen. So yeah, you're right. You can't know. But yeah, so my recommendation is never use the pre-increment or post-increment operators, which we just wrote, inside function calls. Don't ever pass a pointer to a variable inside a function call in the function call if you use that variable somewhere else in your function call. It's going to result in nonsense like this. And so what I would recommend doing is if you really want to increment this, pre-increment first. And then we do actually have to assign a new value. Well, no, I mean, we can't really get the old value now, but that's a good thing. This is never something that you should actually be doing. So yeah, this is a big no-no. Don't do this. And so yeah, that is kind of the last thing that we're going to leave with today. And you can think of these implementations of pre-increment and post-increment here as, well, how your C compiler is really doing it. Your processor probably has instructions to do these things. But yeah, you're going to get this same weird behavior, right? Because of right to left evaluation. And Lusket says we could use pre-increment and parse A-1. Yeah, we could do that. But my point here is that you probably shouldn't. You should really save values in auxiliary variables or do your pointer manipulation somewhere else, because this is just not the way that we want to go. It leads to all kinds of confusing, terrible, disgusting bugs. And this is actually really the last thing that we're going to talk about today. So we're going to talk more about pointers tomorrow. Tomorrow is going to be talking so much about pointers. We're going to learn about arrays and strings in C. It's going to be great. It's all of the like weird pointer stuff in C all rolled into a day. It's going to be really fun. We're going to write some really cool code. We might actually write some code that generates some pretty pictures tomorrow. So we've got that to look forward to. But now I'm actually just going to leave the stream running for a few minutes. And the reason that I'm going to do that is I actually want to test something, and y'all can watch me test this. I want to see, remember that old C compiler for MS-DOS that we played with yesterday, Boolean C? I kind of want to see what it's going to do. I want to see what its evaluation order is. I really want to see where this thing started. So what we're going to do is we're going to play with Boolean C again. And let's get, when am I live tomorrow? So these streams are going to go from 12 to around 2 every day of the week for the next 2 weeks. The goal of these streams is to prepare my students for a class that they're about to take that's going to be in C. I'm a teaching assistant for a data structures class in Java who has also done these C lectures for the past... Oh geez, is this my 4th time giving these? Yeah, so I gave this lecture to my cohort and then the 2 cohorts in the past year, now y'all. So yeah, this is the 4th one. And yeah, it is Central Time. Yes, sorry about that. Should have clarified. Yeah, noon Central Time. Yeah, 12 p.m. Central Time. I'm in the Central Time Zone, so yeah, that's what we're working with. All right, so yeah, so I'm gonna leave. Yeah, if anyone has any questions about anything we talked about today, please feel free to ask in the chat. You know, the chat is for questions here, so yeah, ask anything you're confused about, and you know, while we wait for questions, I'm going to see what on earth this old compiler does. So let's see here. We're gonna go to my C drive, and is this function actually? This should actually just compile in Boolean C. So what I'm going to do is actually just copy this real quick. So let me, here, I'll put up the pointer review while I do this. So yeah, here's all of our notes on pointers. And this is just so you don't see everything that's on my file system, because I do have things that you probably couldn't see. It's not anything weird, it's grades. Let's see here. So we're going to go to our folder that this is in. Where is this? Okay, it's in... Right, okay. Lusket, you only learned about pointers in C++. It's mostly the same. It's exactly the same. So C... Okay, so yeah, Prince Logic brings something good. You thought C was a subset of C++. C++ is what we call an imperfect superset of C. So C++, by and large, shares really the vast majority of its semantics with C, but it actually does break compatibility in a few ways. And so yeah, so C++ is an imperfect superset of C. It's C plus all kinds of features. I mean, just ridiculous stuff. C++ is crazy now. At least it has modules as of C++ 20. Oh, and XISZ, yeah, what's the way to access the notes? And are VODs saved? Yes, VODs are saved, and actually every day after the lecture, I am uploading these notes to the cloud, and I put a link to those notes in the VOD. So in like the caption section, the description of the VOD, you can find a link to the notes. Or I can actually go ahead and upload this real quick right now and give you a link. Yeah, let's just go ahead and do that while we're also playing with Boolean C. We'll actually do useful things while we mess around. Let's see here. Got to go to my DOS folder. Go ahead and dump that there. Let's get rid of int sizes, that program we wrote yesterday. Okay, cool. So let's go ahead and switch back. Oh, hello, share menu. Let's go ahead and go back to our screen here. Pull up DOSBox. All right, let's make sure that I can see that file. DOSBox used to have problems where it wouldn't actually reflect file system changes. Oh, and it still doesn't. That's really annoying. Okay. I'm going to unmount and remount this then. Unmount drive, remount, C, documents, MS-DOS. There we go. Okay, cool. Oh, the file name is too long. There we go. Oh, gotta run my auto exec, and we'll launch Windows. There we go. Can everyone hear that ding ding? That's a sound called ta-da that is like permanently burnt into an entire generation of computer users. It's not my generation of computer users, but it's pretty famous. Anyway, let's go ahead and open a file. Go to our C drive here, open fun.c. I think this is just going to compile. This should just straight up compile and run. It really should. Okay, so let me put this back to pre-increment real quick. Okay, so yeah, we're going to do pre-increment. And let's see what happens. So if evaluation order is left to right, then we're expecting to see 7, 8, 8. And if it's right to left, we're going to see 7. We're going to see 8, 8, 7. Let's run it. There are errors. What do you not like? Oh, right. Yep. This is an old compiler. Right. Okay, fine. Here. You can go up. Can you cut and paste in this? Oh, cool. We actually have normal accelerators. That's interesting. I didn't know that we really had those accelerators this time, but we do. Cool. Okay, let's go ahead and try this now. Oh, don't use tab. Control K, S, run. Oh, interesting. Okay, it's right to left too. Wow. Okay. Huh, that's interesting. I'm gonna have to play with this. I'm gonna find a really old C compiler and we're gonna watch it tomorrow on stream. Okay, we've got some questions. What would be the use to learn C? Wouldn't it make sense to just learn C++? Well, not really. So, again, some of the semantics do differ, and so it is important to learn the language you're going to be working with. My students are going to be working in C for their class, so that's why we're doing C. I also, just as a personal preference, happen to prefer C. C++ is a big behemoth, and I work with C++ at work, and it's an interesting language, but, you know, it's, first off, it might be too complicated to teach just on this stream series. That would be a stream series that would take half a year to teach. But also, yeah, we want to teach the language that we're going to be working with. In future days, we're going to cover the C standard library, which is very different from the C++ standard library. We're going to talk about things like structs that have different semantics, arrays that have slightly different semantics. So yeah, the languages are different enough that we can't just teach C++ and map it down to C, unfortunately. Not trying to tackle all of C++. Tried it once, didn't end well. Yeah, C++ is kind of scary. Yeah, Prince Logic, C doesn't have namespaces. We're gonna, if you want namespaces in C, you're just gonna prefix your functions. Oh, and char arrays are fun from XISZ. Yep, we're gonna talk about that tomorrow. We're gonna learn about how strings work. It's gonna be great. You're going to wonder why this was ever a thing that people did. So anyway, yeah, so Boolean C turns out uses right to left. That actually, so this is a C++ compiler, and that may be a C++ thing. We'll see. Oh, Lusket, all right, well, have a good night. I'm glad that, yeah, I hope that you were able to learn something or at least enjoyed the stream. Yeah, have a good night. Hope you can tune in tomorrow. We'll be doing some more interesting things in C, some things that are a little bit more fun than just blathering about pointers for a while. Okay, so yeah, I'm going to actually keep it open to questions. You can continue to ask questions, and I'm going to look up if this is a C++ thing. This actually might be a C++ thing. C++ argument evaluation order. Let's see. Oh, it's unspecified. Okay, cool. All right. Awesome. Yeah, as of C++ 17, it is still unspecified. So there you go. So yeah, we still don't know. We still don't really have a good answer to that question. Okay, all right. Well, in that case, if we have no more questions, I am going to end the stream here. We spent some good time today. I hope that everyone was able to learn a lot. And yeah, we'll be back again at noon Central Time tomorrow to talk about some things we can do with pointers. We're going to talk about arrays. We're going to talk about strings. We might talk about structs. No, actually, we're not going to talk about... Well, we might talk about structs. Yeah, and then that's probably what we'll do tomorrow. So yeah, everyone, take care. There's my nice Windows 3.1 sign-off sound. The notes for today's lecture will be posted in the description of the recording. And actually, I can just go ahead and very quickly upload these and share them with you now, because I'm realizing that people on the stream obviously don't have access to the course page I'm using to communicate with my students. So let's see here, include page background, no handwriting recognition, export. We're going to export it to Google Drive. Let's see, the iPad's not visible, right? No, it's not. Okay, great. We'll just give you the pretty C-line window. Upload to Drive. Okay, go ahead and upload that. All right, so yeah, so all of the course notes for each day are being posted as a unified PDF. So they're just one kind of big document that you can access. It is accessible via the link. I don't care if you share it with people. I'm completely fine if you do. That's kind of the point, actually, is that this is generally useful to people. So let me go ahead and get us a link. So anyone with the link, copy that. All right, and here you go. In the chat, here is a link for the notes. Yeah, there you go. So yeah, the VOD will be up soon. You can rewatch anything that you're confused about. You can access the notes there. I'm probably never going to take these down. I got grandfathered into infinite Google Drive space, so that's kind of cool. So yeah, everyone take care. Have an awesome day. Prince Logic, that's a good idea. Post it in the channel bio. I will do that. I will do that. But all right, yeah, for now, take care, y'all. Have a great day. See you tomorrow.